Okay, well, thank you very much for this introduction, Linda. Yes, I'm Dr. Jonathan Chambers. I work in the Energy Efficiency Group, and I'm here to represent an elephant. Which elephant? This one. Heating is perhaps a bit of an overlooked topic in energy systems research, even though, at least in the domestic sector, it represents about 60% of energy demand. So every time we talk about clean energy in terms of electricity, when it comes to buildings, that's actually a minority of the total demand. And in Europe, most of this still comes from oil and gas. Also, about 60 to 70% in Switzerland is from oil and gas in Switzerland. So this is a major topic to be addressed. If you think about buildings, I mean, you walk down any given street, more than half of those buildings, we will have to do some kind of intervention in the next years to modify them in some way to end the dependency on fossil fuels and reduce their carbon emissions. And that's huge. In Switzerland alone, we're talking about 2 million buildings, so about a minimum 60% of them we will have to do some kind of physical intervention on those. And that means we cannot do this without moving beyond the individual building. And the way we move beyond individual buildings is the thermal grids. So the idea of a thermal grid is that instead of trying to replace every boiler producing heat in every building individually, we connect buildings together with a thermal network, with a transport fluid, which is almost always water these days, that can then draw energy from a centralized location, which we can then inject with renewable energy. Which could come from, example, heat pumps providing heat, which could come from a renewable energy source, which could be, for example, a geothermal source. It could come from lake water, such as we have projects in Geneva that can do this, and so on. It can be multiple sources as well, so we have more flexibility in terms of the energy sources. And we also have more flexibility in terms of how we manage the supply, because we have a system which now has also, for example, thermal inertia, so we can match better the supply and the demand, so we can have also a very good interaction with renewable electricity supply by trying to match a bit peak loads and so on. We can also do things like here you see a bit in this illustration, it's from Angie, I wish I could draw that nicely, where we have, you see a bit industries, you see a bit services, we see residential, so they have different needs a bit at different times, so we can do all kinds of balancing and management with that. So it's a really interesting technology. It's not actually a new technology. I think the oldest thermal networks are probably Roman from using heat from thermal sources, so this is not new, but it's also probably the technology of the future if we want to develop renewable districts. And so we want to know a bit, how much is the potential actually? Because now we're moving beyond individual buildings, we have to understand something which has, a spatial aspect, an urban aspect. How much is really the potential for this? What does it depend on? These are many different questions. These are big investments, these are big infrastructures that we're proposing. What's the potential? Who's going to build it? There's been a bit of a review on some of the potentials. We see any estimations from 1.2 times to 4 times the present day. So these are huge variations because we have different methods, different assumptions. So I'm going to explain a little bit about how we've approached this in the Energy Efficiency Group at Geneva so far, and a bit about what our observations were from this process, and finally, some of the outlook of what we're working on right now and in the future. So a classic method for doing thermal energy grid potentials is you just look at the energy density per hectare. You set a threshold, you say, okay, in this hectare, in this region, we've got about 500 megawatt hours per square meter of total demand from all the buildings, and we'll build it there. The problem is that all these thresholds are only based on past projects, most of them on countries which were early movers in this space, so particularly Sweden and Denmark. We've looked at their projects, we've said which projects there did they build, what was successful. We'll learn some, it's sort of manual machine learning, since this is a machine learning conference. We looked at these things, we learned some thresholds, and then we applied it. There's a problem. We'll only build what we predicted, and then we'll only observe what we predicted we would build, and then we will only continue in this thing. We will never do anything new, basically. We will never challenge any of the assumptions that underlie these things. And when I've done my own research, when I've done my literature reviews, you can see these thresholds, they go back 10 years, 15 years. And they've just been repeated and then reused in projects, and then new projects have cited the project before, which cites the project before that. And then these have never really been challenged, actually. And we don't actually know if these are very good. We know you can build with these thresholds successfully. We don't know if we can only build with these thresholds successfully. We don't know if there's any other approaches. So the first thing we tried was to move to more multi-criteria model. So here we use the fact, especially in Switzerland, we have very good geospatial data. We have data about individual buildings, and we developed these data sets on a pixel basis. And we developed still a relatively simple model, but that's at least based on 3 criteria instead of 1, that we have a certain number of buildings, because it's hard to build a network when you've only got 1 building. We need a certain demand per hectare, but we set a relatively low threshold, so this is just a sort of sanity check, that it's not just a building, but it's an empty barn that no one lives there. And we also developed a method to roughly estimate for each hectare how much pipe would you actually have to build in this hectare to connect all the buildings that are there. And then you can get at least a linear heat density. And now linear heat densities, when you build thermal networks, are really important because all of your losses, all of your pumping of fluids are based on how much energy you're pushing through how much pipe at a given amount of time. So that's more, starting to move towards a more bottom-up understanding of the actual system we're trying to model, so we can start from its physical principles, but move into a kind of data science approach where we can then use a physical basis, an engineering-based model, but do it at the level of a whole country. So here we can basically use this method. We get Boolean rasters, and then we do a bit of post-processing, and then you can just about see in orange, you get some regions where you say, okay, in this regions we think district heating is a good idea. And actually, it's a lot. So we published a paper about that a few years ago. We also published the data set, so they're now available online on the University of Geneva's Open Data Archive service, long-term data archival service, and there's a short paper from the CISPAT of last year that describes that. So these slides will be available. If anybody's interested in that data, they can have a look. And that gives you basically a vector of data per pixel with a lot of different information about the building stock characteristics per 200-meter pixel. So you have the number of buildings of certain by type, by age, by their energy demand. And so you can do different aggregations, disaggregations. You can see these are basically 3 different views across that whole data set. And another thing we actually have in there, and this was probably the slide should have been before, we also want to think a bit about how much energy you could save, because of course you're increasing the supply or changing the supply. You're also saving by having building renovations. Unfortunately, building renovations are extremely expensive in Switzerland because labor costs are very high and they're the main input to any renovation. So here we see a bit potential savings, which are really big. I mean, you can see more than 70% in some areas. You could save energy. But then it's also a big question of how much of that is actually going to be happening. So we did, going back to a bit what Evelina was saying, we did some scenario analysis. What if we apply all of the savings? What if we apply none of it? To explore a little bit these different aspects. But what's interesting, I think, with the map is that you really see the strength of doing this GIS, this data science-driven approach, is you see the spatial heterogeneity of the building stock. That some areas have old buildings which could be very much renovated. Other areas have new buildings or have already been renovated. So you have a lot of variation that then is also driving your outcomes of the model, but also, of course, a lot of uncertainty as well. And that's very challenging. So the results of all of this, we estimated you could supply about 60% of all of the heating demand in Switzerland with thermal networks. We did a bit of validation. We worked with an energy services company that was designing a thermal network for Brieglis, actually. So we have at the top the plan they did basically by hand. So they went into the town, they discussed with the stakeholders there, and then they drew basically based on what they knew of in detail of the region, where they thought they could put these types of networks. And below, you have overlaid their plan with our automatic model, and you can see that we basically reproduce what someone would do by hand. So we can validate against an expert input, that's great, but maybe it's also a bit of a problem, because maybe we're still just reproducing our basic assumptions. And this is something which we're now trying to wrestle with. A big problem with this kind of work is that actually when you take the input data, the energy relevant data, it's rarely collected for the purpose of modeling. Usually, for example, when we talk about energy bills, that we need a lot if we're going to do energy demand estimation, energy bills are not collected to produce nice data sets for energy research scientists. They're produced to charge people money. And maybe they bill, they can have all sorts of different boundaries, what they bill, what is included in the bill, who is included in the bill, that don't necessarily match up at all with what we want when we do the energy analysis. So we have a lot of complexity and uncertainty that comes there. As a result that it's so complex, we tend to over-rely on what we found before, because it's so hard that when someone comes up with a number for something, you just say, I'm just going to use that. Someone published it, it got peer-reviewed, it must be fine. But then we never necessarily challenge these things, and it's a big problem when things change. As it's been mentioned before, 3 months ago, we didn't think we would have an explosion in gas prices. All of the models which were saying, okay, well, everything you're building is competing with gas, that is now really, in terms of heating, which is where gas is one of the main uses, that changes a lot of the calculus here. And that's really challenging when you have fundamental changes. But what we can do, which helps a lot, is that we know, at least in sort of a smaller case like this, when we're looking at specific technology, we know that all the processes are based on physics and engineering principles. We know that there's like a basic physical principle and an engineering system which drives all of this, and we can use that. And so this is an approach which I've been using a lot also since I did my PhD, actually quite a few years ago now. We call Greybox Modelling, something I already used in the past precisely to try and bridge this data science approach, which tends to rely a lot on what we know from the data we already observe, and the pure statistical methods, so which is a pure statistical method, so that's kind of very classic machine learning. You have some data, you put it into a statistical process, and then you get some predictions or classifications out of it. You have sort of white box modeling, which is purely theory-based, theory-driven. So this is classic engineering models. This is really bottom-up. People may be familiar with programs like Transys or similar, where really you have a full simulation of the whole thing, but it's very heavy. It's hard to integrate large data sets. It's hard to sort of harmonize with many different data sets. And so we end up with sort of gray box. We mix a bit the two. We try to integrate the physical principles into a statistical model. And this allows us to kind of bridge a bit these different worlds, to try and integrate, things like the physical limits, the basic fundamental principles of what's going on, with a data science approach that allows us to work with large data sets, that ingest data sets which are not originally designed to be used in specific physical models, or to apply something at much larger scale. So we're no longer modeling one system, one building, we're modeling countries at a time, but still at a resolution of a few hundred meters. And this, I think, is quite powerful. This is something that we've now started to use. This is a bit our ongoing and future work, where we've said, well, look, we've got big data sets, we've got big computers. We don't need to stick with pixels. We can really model individual buildings and how they're connected together, and we can do this at scale. So we've developed some novel acceleration techniques, so algorithmic approaches that allow us to do this kind of modeling at reasonable speeds. So you can really do the kind of analysis, and also especially we want things to be fast because we love to do uncertainty analysis through Monte Carlo. So that means not just running a model once, but running it 2,000 times, 10,000 times maybe. And we're developing this system that allows you to do simulation of many possible network variations. You can change assumptions, powered by all these large GIS data sets, to really do thermal network grid modeling at the building level. And this is a project that is actually now supported by InnoSuisse, where we build a tool for designing thermal grids. So you see a little bit like this is the output that it can produce. This is actually something it can produce in a few seconds, where you selected a set of buildings, you tell it, I want to build a thermal network with these buildings, you give it some criteria, and it will draw for you a thermal network. And it's fast enough that we can do this anywhere for any number of buildings, and try to then really get to the bottom of this potential to really break out of our sort of historical assumptions of what can and can't be done. So really that's the status now of our research, and we're working on that now. And that's all I have for today. There's a brief summary, as I said. Thermal networks, I think, are really an essential part of the energy transition to address something, to address the needs for heating and actually eventually cooling. I didn't have time to go into that. That is really a big part of energy demand today, something which involves a lot of physical changes to our environments, our everyday environment, to the buildings that you live in. That such a big change means adapting to disruptive technology, to new kinds of technologies, breaking out of our own assumptions, that we can use Greybox modeling as an approach to kind of marry these statistical or past data-driven approaches and our physical understanding of the systems that we're designing, and then briefly this novel thermal grid approach that we're working on today. So thank you very much.
Thanks for the nice presentation, Jonathan. Who has a question from the audience? Yes.
Thanks for the presentation. My question is, what's the most challenging part of installing these thermal networks? Is it building level renovations? Is it putting the pipes in the ground that connect the buildings? Or is it the plants?
So I would argue probably none of those things. It's getting people to agree to it in the first place. And this is also part of our work and why we're also interested in diving down to the building level, because what happens when you start building things at the district level is you have a lot of different stakeholders. When you were just renovating one building, you have to convince the building owner. If you're lucky, they're interested in environmental issues and it's not too much of a problem. When you build a network, you have to basically follow the trace of your network and see who are all the people who you're going to connect to. And each of those needs to accept to join the network, and for the network, say, business model to work, they also need a certain number of customers. So that's probably the most challenging. It's obviously not by itself a data or even an engineering problem, but I do think that being able to do this kind of detailed modeling can help, because you can put these plans in front of people a lot easier, a lot less cost. You don't have to sort of convince people, then say, okay, now you're sort of interested, we make the plan. Then you look at the plan and then decide if you still like it after all. We can do this in a much more iterative process, and that's one direction we're going now with that work.
Very good talk about this district heating, which is a bit, I'm coming from the electrical grids, it's an interesting different field. In electricity, we see that many consumers now turn into prosumers because they have a PV or they have an electrical vehicle which can also do demand response. Do you also see something like that in the thermal grid, like a factory who has some process heat and that also more producers also enter in this grid, so it gets a bit more decentralized?
Yes, that is something we see increasingly. So again, for interest of time, I avoided going into too much detail, but there's actually several generations of thermal grid topologies. Traditional ones are very much centralized. Now we're talking about more low temperature grids, which allows different people to inject heat at different points. Then, of course, you do have things like thermal management problems. I think a lot of the issue in heating is not so much, what's going on, whether you have multiple prosumers. It's the fact that actually the investment in the level of control of heating grids is a lot less. Electricity grids, everybody understands the needs to have stable electricity grids. There's a lot of modeling, a lot of control theory, a lot of hardware that allows that to happen. In thermal grids, as soon as you want 2 sensors instead of 1, people are like, oof, that's a lot. It's very expensive. So this is perhaps a bit more the challenge, is kind of convincing people that it is an important investment and you have to put money into it, basically.
Okay, thank you.
I'm not sure if I read the map correctly, but you showed the map with a potential where this district, this thermal heating could be implemented. Can you show it again?
There was 2 maps.
Well, yeah, there were more actually, but
this one is only the energy saving potential in the buildings themselves.
Ah, okay.
I actually don't have the map of the networks because it didn't look very good.
Okay, because then I was surprised because I would suppose that that's a mountainous region and building a network in a rock would be much more costly than just regular soil. So do you actually take into account the cost of building the network in different soils?
So at the moment, no. That's part of the new work, exactly to try and estimate these things. It's also something where we have very little data. Most of the information, as I said, comes from past studies, which are usually in Denmark, actually, and Denmark has no mountains. So we don't have information on this. Then you can go to suppliers. Every supplier will quote you a different number. We honestly don't know. They can be done. I think what I have done is another work actually was doing a little bit more sensitivity analysis on these models and their costs. In the end, the actual cost of the pipe network is not necessarily the majority of the cost of the whole system because they have very long lifespans. So when you annualize it, yes, you have to build a hole. Maybe you dig it into rocks or difficult ground, but then it's there for 40 or 50 years. So it's often not the biggest challenge in terms of costs over time, although it can be a challenge for the costs up front, because of course if you tell look, it's going to be 50 million, but don't worry because you'll pay it in 50 years time, they're like, yes, but I still need 50 million today, which is a different story. I believe this is the actual thermal network, we're just in a region.
Actually, just following on from that question, energy saving potential, you used building archetypes to have predicted that. Is that based on the whole building fabric and system and potential supplies of storage, or is that based on very limited kind of data set where the foundation lies?
So I actually apologize to our ex-PhD student who made this. I should have cited his paper at the bottom, but he did his PhD only on the archetype-based energy saving potential, which is based on individual fabric elements. So it's the potential to renovate walls, roofs, windows, and so on, per building archetype, also divided by region, and then by building age and so on. So it's a detailed thermal balance model here.
Okay, I suppose there is also the heating system that can be upgraded, for example, the delivery efficiency.
Yeah, so he actually split it. So this is the work of Kai Streicher. If anyone's interested, I can put the reference that I should have put here. But he was able to divide the energy demand into the useful energy demand, so the purely thermal demand, and then the heating system. So this is only looking at the useful need for heat. Then we could, in a second step, add the actual the heating system. So of course that makes a huge difference if you've got an oil or gas burner at 90% efficiency or a heat pump at 300% efficiency. That would be separate. But since this was only looking at the useful energy need in the context of building a thermal network, which will provide all of your useful heat, this part's only looking at the heat requirement saving, not the final energy for the heating system.
Okay, thank you.
One final question from the audience.
Thanks, Jonathan. So you spoke a lot about the case of Switzerland here, and I wonder for these types of methods, if you think of the, so to say, business potential internationally, where does it lie and how big is it?
So all of the work today has focused mainly on Switzerland because we have convenient GIS data sets which match. So all the codes, all of the sort of coordinate systems are matching. In theory, we can use this anywhere where there's reasonably good building data. And this is actually an interesting development in the last couple of years. In Europe, there's been a big push for this kind of open data. In French, they call it cadastre. For example, now in France, you can get a very high quality one comparable to Switzerland. So that it does increase a lot the geographic potential reach. now that you exactly have this big push for open data, because I think a lot of governments have understood that there's a lot of potential in research and industry innovation by having this as accessible. So yes, I think there's a lot of potential going forward and interesting geospatial data sets that could be used.